ado, Logan Campbell.
All right. Make sure my mic is working. Sounds good. Thank you so much. I am very excited to be here and to talk to you guys for the next couple of hours about drone survey accuracy and how to prove it. And honestly, a whole bunch of other ancillary topics that will actually go into the broader idea of using drones in land surveying. So to just jump right into it, first of all, my objective today is a couple of things. First of all, I want to make sure that I give you all enough information in this presentation to understand exactly what drone surveying accuracy is. Because there's a lot of misconceptions. There have been hundreds of different definitions of accuracy over the years. And in fact, I guarantee that not everyone in this room has the same exact definition of what accuracy actually means. We're also going to teach you how to create and interpret different accuracy statements. So when you see an accuracy statement, you know what it actually means in practice, or on your own drone surveys or other surveys that you touch, how to actually create certified accuracy statements, how to certify accuracy when you need to, that sort of thing. We're also going to go an awful lot into all of the different things that impact accuracy. So if you think that drone surveys are inaccurate, you know why they might not be inaccurate, because there honestly are a lot of ways to do it wrong, but you absolutely can get very, very accurate surveys out of drones as well. And also, I want to help give you information about where to go if you need more information. Because accuracy, like many different topics in the world of surveying in general, is actually really, really complicated and goes way deeper than I could possibly go in 2 hours, because it does venture into the realm of science and statistics and field testing and all of these things that are unproven when you get to difficult sites, difficult conditions, all of that stuff. But I want to make sure that I also provide enough resources of where you can go if you do need more information about drone surveying accuracy and all of that good stuff. So as a little bit of background here, I mean, I know they read out the bio, which was always weird hearing my own bio even, but whatever. Yes, we have been, Aerotas as a company has been doing drone surveying for land surveyors and civil engineers for coming up on 10 years right now, which makes us not that old in the world of surveying, but kind of ancient in the drone world at least. So the way that our company has worked, we work with surveyors all over the country that fly drones, send us the data, and our team of photogrammetrists, GIS techs, LiDAR techs, CAD techs, etc., actually do all of the mapping. So as part of that, we have learned from a volume of data that very few others have of tens of thousands of drone survey projects of what actually makes a good project, what makes a high accuracy project, what one can totally ruin your accuracy, and how to get good accuracy. A little bit about myself. I come from a background of statistics, and that actually makes me one of those super weird masochistic nerds that totally loves talking about statistics and accuracy. So I apologize in advance if you don't like math that much. I'll try and keep this as math light as I can, but statistics and statistical analysis, which bleeds into how do you actually measure and report accuracy, is totally my thing, and I kind of enjoy talking about that. But even though my academic background is in the statistical side of the equation, because this clicker seems to be a little bit unreliable, so I might have to push a button. As a company, we are not an academic research company, we are actually a business. And our company objective, and the reason why I'm here today, is not just to teach you a bunch of math formulas or read off of a PDF, but actually help you apply the concept of accuracy from a really detailed academic perspective. But then how do you actually apply it in the world, in the real world? How do you use these accuracy statements in a sense that makes you more confident with your data, makes your customers more confident with their data, make sure that you can get everything right without breaking the bank or needing to hire a PhD statistician to run all of this. So to do that, we think that a good drone program ought to do three things. It should save you time, it should save you money, and it should get you better deliverables. In our opinion, if your drone program isn't doing all three of these things, then it's not working. So my goal is not to come here and say, for every drone survey, no matter how big it is, you should spend at least 3 days in the field shooting check shots so that you can validate your performance. Like, no, that'd be absurd. You can't spend 3 days shooting check shots just to validate every single drone survey, or you'd never use your drone. And so my goal is to tell you where the standards lie, and then also bring it back into the real world so that it's actually something you can use, so that you do get better accuracy, you know what to do to certify it if you need it and go from there. And so in order to do that, we are going to cover a couple of kind of major topics over the course of the next 2 hours. First of all, what is accuracy? Which is actually a way thornier question than you might think. We are also going to talk about what impacts accuracy and a number of best practices in order to keep your accuracy as high as you need it to be. Not as high as it can be, because as I will talk about, getting accuracy as high as it can be or as high as possible is so stupidly expensive that you would never practically want to do it on a project. So there's a spoiler alert to before. The best accuracy possible is not what you should be targeting. You should be targeting the right accuracy for the right cost for the right job and that sort of thing. We will also be talking about how do you measure accuracy. It's all good to say this is a very accurate project, but do you actually know? Do you measure it? Are you measuring it the right way, making sure that that is all done properly? As well, then, towards the end, we're going to be talking about how to certify and report your accuracy, ranging from just a little bit of information in the metadata of the map that you produce, all the way up to formal certification statements that are good enough for the most rigorous academic standards or government standards on any aerial survey, drones, or otherwise. But it's also important to talk about a couple of things that I am not going to be covering today that you might have questions on, and there are answers to, and heck, I might even be able to answer them, but that's not what this talk is about. First off, I'm not going to be talking about large format stereo photogrammetry. For anyone that works in photogrammetry as much as I do, the traditional methods for stereo photogrammetry have a lot in common with modern digital photogrammetry, but that's not what this topic is going to be covering. Even though there's a lot of overlap for how accuracy is measured and the things that impact this, I'm really going to be focusing today much more on the more common and growing side, which is digital drone-based photogrammetry, ranging from your few $1,000 small drones up to your couple $100,000 really high-end drones, but we're not getting into your $1 million metric cameras on manned aircraft, that sort of thing. Same thing with large-scale manned aircraft LiDAR. We'll be talking about drone-based LiDAR, which is absolutely in a totally different category than large-format LiDAR. If you're doing anything from a couple acres all the way up to a few thousand acres even, this will apply. If you're trying to do a LiDAR survey of an entire county, that's actually typically going to be a slightly different set of statements and things that we will not talk about today, as well as some of the other kind of more exotic topics that are very common in the world of academic photogrammetry and aerial mapping, which is things like satellite photogrammetry and synthetic aperture radar, which can be on either planes or satellites or things like that. That technology is borderline magical. It's super cool, but not what we're talking about today. If you really are interested in that, I'll give you the links at the end of how to actually research accuracy certifications on some of the more exotic and rare forms of aerial mapping. But one thing first, I want to actually give you the answers to some of the main questions in this presentation. I don't like to bury the lead and say, oh, how accurate are drone surveys, and then make you sit through 2 hours before I even give you an answer. So I like to start with a couple of just kind of basic answers, and then over the next 2 hours or so, we will dive into what it takes to get to the accuracy of these drone surveys and what it takes to certify them. How accurate are drone surveys? They are absolutely as accurate as you need, and in fact, they are up to 1 centimeter of accuracy. And I should apologize, by the way. I hate all of the academic documents that I'm going to refer to because everything's in centimeters, and that's not how we work. We work in feet, we work in tenths of feet. I'll do my best to talk in tenths and hundredths, but there's enough documentation on the academic side that sometimes I slip up and say centimeters. So I apologize. 1 centimeter, what is that going to be? That's about 3/100ths or so. You can get a drone survey absolutely up to 3/100ths accuracy. And you might be saying, but that's even more accurate than most GPS systems are capable of doing. You're correct. It's possible. It's wildly expensive, and basically you will never, right now it is not practical in an economic sense to get centimeter accuracy. But the idea is that you actually can get crazy good accuracy. There are also a lot of ways to get very bad accuracy out of a drone survey. If some of you are coming in here thinking, I'm here to see the accuracy of drone surveys because I got this drone survey and it was off by a foot, or it was off by 10 feet, or it was off by 100 feet. Oh yeah, there are lots of ways that you can screw up drone surveys and get ones with very bad accuracy. But if done right, you absolutely can get them better. it isn't actually all that hard to get good accuracy. You just need to follow the right procedures, and then at the end, ideally, you measure it so that you know you have good accuracy. So accuracy can be up to a centimeter. I say sub-centimeter if needed. It can sometimes get there, but that's pretty rare. The biggest limitations when it comes to accuracy are time and money. And that's where, again, it goes back to from the academic side, it goes back to the business side of actually trying to get the accuracy that's right for the project, that a customer is willing to pay for, that you have the time and resources and manpower to go and that sort of thing. But to get all the way to the answer, most drone surveys are 1/10 of a foot. In fact, to me, it's a wonderfully round number as well, that it's right around 1/10 of a foot. It's easy to say, it's easy to measure, and that is what most drone surveys should target. If you need an excess of 1/10 of a foot, in all likelihood, a drone survey is probably the wrong tool for the job if you need it to be reliably, demonstrably, provably better than 1/10 of a foot. And if you're saying, well, you know, I'm only getting 1/2 a foot of accuracy out of my surveys, well, we can get a lot better with that. And then to answer one of the second questions, how do you actually measure accuracy? Well, the answer is pretty simple on that. The high-level answer is simple. You set a lot of checkpoints, which are points that you didn't use to make the model. You measure the error between the drone and the checkpoints, and then you report the error. There you go. It's as simple as that. All right, that's all. We're done now. Okay, I'm kidding. The scientific foundation for this, because again, as I talk about the academic side and the business practical side. The academic side is all based on documents by the ASPRS, the American Society for Photogrammetry and Remote Sensing. For those of you that aren't aware, this is basically the governing body almost that certifies photogrammetrists and mapping scientists and aerialists, that has been around for a very long time. They're a nonprofit founded in 1934. And actually, if you are interested in learning more about drones and drone photogrammetry and aerial LiDAR and any sort of aerial mapping in general, this is the organization that you want to be a part of. And they are the source of what really is the gold standard for documentation about accuracy in all aerial mapping. And this is going to be the source of a huge amount of what I am talking about today. The ASPRS Positional Accuracy Standards for Digital Geospatial Data. And in fact, this is very recently released, edition 2, which was released in August of 2023. It is an update after the older version, which was from 2014. That was how we've been doing digital photogrammetry for the last 10 years. And they just recently updated the standards. So this whole presentation is brand new about the brand new standards, which also means you get to put up with it if I don't remember which slide comes in which order and I repeat something or you catch a typo. I apologize, you're all my guinea pigs. You're welcome. But yeah, this is the document that is going to be guiding the academic side of all of the accuracy stuff that I'm going to talk about. Now, the ASPRS Positional Accuracy Standards are in many ways very, very delightful. They're very good. They're very rigorous and thorough. But it's 97 pages long of extremely academic stuff. Not ranging from both the content and just the way that they talk about everything. It is very, very rigorous in terms of its mathematical and procedural standards, almost to a fault. The level that they specify exactly how you must calculate every step of the way to be in perfect conformance, all the way to the procedures that you need to follow when setting and marking ground control points are incredibly detailed and rigorous. The full standards are very complicated and often very impractical to implement. Because it is academic, it is much less worried about the cost of implementing things, although they do provide some acknowledgement to limitations there. But they care about it being perfect, not about it being cost effective. So that's also where, if there are other academics or ASPRS members in the room, I might upset some people because I say, the standards say this, but you kind of can ignore it sometimes because perfectly following the standards is so crazy expensive that no one will ever do this. And it can also be very difficult to interpret. And in fact, to start out, to show you why I'm not going to be just doing screenshots or reading a PDF, I clipped one of my favorite phrases that even I had to read a couple of times through to understand what it was talking about. This is just an example of how this document is written, about point density and vertical accuracy, and about the Nyquist-Shannon sampling theorem and signal processing to determine the point density required to accurately represent project terrain. I won't read through all of it, but the point is if you don't understand what that means, that's okay. You absolutely do not need to know what the Nyquist-Shannon sampling theorem is for determining how far you should set your points apart. I can tell you, I can translate this into plain English, not that this is the most important part of the talk, but it basically says if you have a lot of hills and ridges that are a foot apart, then you should set your point density to half a foot. That's it. Just take your, how big are the features and make your resolution twice that good. That's all it says, but it says it in very academic ways. So yeah, my goal at the end of this presentation today is to take this extremely complex and in-depth topic, which I actually really like. I love the mathematical foundation of it, but I want to make it simple, useful, and practical to you guys. So again, I'm not going to be able to explain all 97 pages of this document because there's so much information in there. I'm not going to make you a PhD statistician in this 2-hour presentation, but I am going to take this and try and make it as simple and practical so that you can actually use this stuff, this information, the next time you're out in the field, the next time you are touching a drone or anything. But it is worth noting, as I get through this and right as I'm about to jump into all the details, this stuff can be really complicated. Please ask questions. I know it is after lunch and everyone's a little sleepy except me because I'm a ridiculous coffee addict and I drink way too much coffee. But please ask questions. I'm here to actually help teach you, and there are things that I might be missing. So I really love audience participation. I love questions. If there's something that's complicated, ask me. I love it. This really is my topic. These are the things that I'm the best about. You won't become an expert overnight, like I mentioned, but you can always talk to an expert as well. If there are questions that you have, ask me, or you can shoot me an email. I'll have my contact information up at the end, or talk to a company like ours where this is the type of stuff we do all day, every day, and we are very much more than happy to help. So with that, let's dive into the first real question of what is accuracy? Now, as I mentioned before, there's absolutely no single definition of accuracy. Surveyors don't agree on the definitions of accuracy, especially when you're talking about accuracy versus precision and relative and absolute accuracy and national map accuracy standards and contour intervals and map scales and all of that stuff. These concepts are very complicated. But what might actually help, especially for those of you that have been in surveying for a while, is going over a really brief history in a single slide of map accuracy standards, what they used to be and how they've changed over time. And from what I could tell, one of the first real formal sources of measuring accuracy that is actually still in use today by a lot of people are the National Map Accuracy Standards that were published in 1947. And in a general rule, this is accuracy based on paper maps, where the accuracy was implied based on the contour interval and the map scale. So if you had a 1-foot contour interval, then that would expect 90% of the things, of the data you check everything should be within half a contour interval, I think. I don't even remember exactly what the standard is, but it's all based on contour intervals and map scales. And unfortunately, it just doesn't really apply to digital data anymore. The ways that we gather data, we don't always print things. It's so trivially easy to turn 5-foot contours into 1-foot contours into 1/10 of a foot contours. So the concept of contour interval as a metric of accuracy doesn't really apply anymore. And honestly hasn't for a while. It then progressed into a much more rigorous standard. In 1990, I think is when the ASPRS published one of their first mapping accuracy documentations, but it was still focused on printed maps using film-based photogrammetry for contour intervals and map scales and things like that. It was in 1998 that the National Standards for Spatial Data Accuracy was released by the government, which switched to a more statistically rigorous methodology. And this is one where it switched from like, your accuracy is 1 foot because you have 1-foot contour intervals, which was simpler, to the concept of more statistical and more probabilistic based accuracy of a 95% confidence interval, where if you say accuracy is a foot, does that mean that 95% are in a foot? So you might actually still have some shots that are more than a foot out of tolerance, so to speak. That's already getting hard for some people to understand because it is probabilistic, but that's where it really moved. And then in 2014, the ASPRS Positional Accuracy Standards Edition 1 came out with, that's been the gold standard for the last 10 years, which is the RMSE, or root mean squared error of independent check shots. And that's really the foundation for what accuracy is today, which is in the edition 2. It is still based almost entirely, I say almost entirely, and I'll get to that in a second, on the error of independent check shots. You measure a point, you don't use that point for creating a map, and then you say, okay, where was that point according to my ground-based measurements, and where does the map say it was? You do that 30 times, calculate the average, and that's more or less the accuracy of your project. We'll get to the caveats, though, in a little bit. But again, it's really, I want to hammer on this part at the beginning that accuracy is probabilistic. Surveyors, I think, are so much more comfortable with this than a lot of your clients that might work in survey-adjacent fields, whether it's a lot of construction folks, too, when they will often say, what's the accuracy on this? And I'll say 1/10, and they'll say, but I found a point that was 0.12 off. How dare you? It's like, well, it's probabilistic. 1/10 means that the root mean square of independent check shots is at or better than 1/10 of a foot, not that every single check shot will be more than 1/10 of a foot accurate. And in fact, we don't actually know the exact error. If we knew there were error, we would fix it, and then there would be no more error. But what we know, or what we are really doing, is estimating what the error is in a world of the unknown. This is where statistics can kind of get weird in terms of what you expect. But I mean, there is an error. There will always be a spread with every technology that we have right now. There will be error caused by 1,000 different sources, and our goal is to estimate it and report what that error is. And it comes across a standard normal distribution, right? This is your classic bell curve that in a perfect world, you would take an estimate of a point, and 90% of the points would be plus or minus a certain amount. And some bell curves are fatter than others. The wider, the fatter the bell curve, the lower the accuracy. That's generally what it means there. To get a little bit more funky, though, on the statistics side, this is what a perfect error histogram would look like. This is what a lot of error histograms look like, where you actually have most errors are right around that mean, that kind of 0 level. But not all errors are normally distributed, and this is especially true once we get into the LiDAR side of the equation. Photogrammetry, and LiDAR actually for that matter, on hardscape is typically always going to be normally distributed. That means if you take a shot on hardscape and then you measure it via photogrammetry, that if it's, call it 100 feet, it might be 100.1 or 99.9, and it's equally likely to be 1/10 high or 1/10 low. But when you get into things like LiDAR and vegetation, you often have a lot of issues, particularly with things like grasses, where the aerial map will measure it too high. Call it, one of the hardest things to actually measure with super high accuracy from the air is dense, low grasses. If you have 1 foot of very dense grass, it's really hard to find what the true ground is. So you're going to have a lot of shots that are a foot too high because it measures the top of the grass. And you're going to have basically no shots that are a foot too low that would put it a foot beneath the ground. And then you're going to have actually a lot of shots as well that are right on the ground. So you have this non-normal distribution, what would be known as skew in the statistical world, that is very, very common in anything vegetated, whether it's photogrammetry where you're trying to interpolate with vegetation, or in LiDAR where it's actually penetrating vegetation. Just being aware that that it's not normally distributed can help you so that you can find these errors and at least report on them. We also want to talk real quick about the difference between accuracy and precision, which I will use those words actually very, very carefully in this presentation. Accuracy is how close something is to the truth, and precision is how close something is relative to itself, this one in the top right. So, for example, the easiest way to talk about this with surveyors is if you take out a total station and you set it up over an arbitrary point, call it 5,000, 5,000, and measure everything relative to that, that survey is going to be incredibly precise. It is precise because everything measured relative to that total station is going to be perfect, near perfect, relative, it has its own error too, relative to where you set up that total station. But you set it up over an arbitrary point. You just made up a point and called it 5,000, 5,000. It wasn't on a known datum. It's not anywhere near, it's miles off of the actual known coordinate systems. And so it's not going to be accurate at all. It's going to be very precise, but not accurate. And you can actually have the opposite thing as well. Whereas if you use if you try and do an OPUS rapid static solution where you have a 50-mile baseline distance and you only have a 15-minute occupation time, that will be fairly accurate because it'll get pretty darn close to where you are on the world, but not precise because it might have a couple of, those exact circumstances. It might be plus or minus a foot in any direction, but it's going to at least be very accurate. So it can be both of those things. As a general rule of thumb, the way to get precision is to use RTK or PPK to a local base station. That means having a base station that you set up on the site that connects to the drone, again, either through real-time or post-processing. That's the best way to get precision, whereas the best way to get accuracy is using things like ground control points that you have longer occupation times, where a local base station is over a known point, or like I said, things like OPUS solutions, or correcting it to a known base station, something like that. So accuracy versus precision actually matters. We're talking about the positional accuracy standards, so most everything that we talk about today is regarding accuracy, but a lot of it can apply to precision too, and that actually will be the last that I think that I talk about accuracy versus precision here. Any questions so far about accuracy? I know I'm going to get out of the statistics stuff soon and get into it, but I'm not getting out of it yet. So I talked about, what is the best definition of accuracy? And the best definition of accuracy is measuring the root mean squared error. Accuracy and error are not technically the same thing, but in practice, if you measure the error of a set of known points, that is what people colloquially will refer to as the accuracy, is same as error. And the way to do that is this RMSE, root mean squared error, and here is actually the formula for it. Very similar to a standard deviation, except it's not a standard deviation around the mean. There are a million softwares that can actually calculate this for you, but you can do it in Excel. Just Google it. It's actually not. This notation is intimidating to a lot of people, but basically it's the sum of squared error between the map accuracy and the survey accuracy. Now, implicit in that is having surveyed accuracy and map accuracy on the same points, right? That is really the core of how to get measured and reported accuracy. Is you need independent checkpoints, not ground control points, independent checkpoints, and then you find those points in the map and you calculate the difference. But where it gets a little bit more complicated now is that drones have actually gotten so darn good with accuracy that we realized that this is a really great idea, except the drones in many cases are getting better accuracy than the tools that were used to survey the points on the ground, right? Because anyone that works here knows GPS itself is not perfectly accurate, right? It's not accurate down to a few thousandths of a foot or anything, though I've heard people that thought it was. If you think GPS is accurate to a few thousandths, you might want to talk to someone that sold you your GPS, because it's not. So the newest way, this is one of those things that's brand new to the new standards, is you actually have to combine these two sources of error. The error of RMSE sub 1, they call it, which is the error of the map to the checkpoint, and then RMSE 2 is the error of the actual check shots themselves, which means that one way to think about it, you are never going to get a drone survey that is more accurate than the ground equipment that you use to measure your GCPs and to measure your check shots. That's one way to think about it. And if you have terrible ground data, you're not going to have very good aerial data. And in fact, we've seen this before with some people, not in Wisconsin, but other states where I have no idea how they got their survey license. People will take ground control coordinates just using the GPS on their phone. And they'll send us ground control points where they'll set a target, because we tell them to set targets, and they put their phone on top of the target on the ground and hit like record a point and send that to us. And obviously we can see that in an instant that's like, this data is terrible. This is not ground, like this is plus or minus 10 feet. And so the accuracy of that map, even though it was actually flown with like a $40,000 LiDAR unit that was using RTK, we post-processed it to a local base station, but we're like, we can't verify any of this because the ground control is so garbage. So that's an extreme example, but in normal conditions, you are still going to have, you know, typically at least a centimeter of error in your GPS, usually a little bit more, at least a few hundredths, and that contributes to the total overall error budget of a project. So this is one of the formulas that when we get to the final reported accuracy, you actually start with the accuracy of the GCPs to the measured, or of the checkpoints to the measured map rather, and then you combine it with the check shot and GCP error that you would get from knowing the ground control system you use. I will point out, I'm not going to be getting into how companies like Trimble, Leica, Topcon, et cetera, calculate the actual error inherent in their systems. That's a little bit beyond the scope of this, but almost all of them will have reports of what the error is depending on whether you use a virtual reference system or anything like that. All right. Another thing to continue on with accuracy is noting that accuracy has multiple dimensions. People do often want to say this project accuracy might be a 10th, but we live in a three-dimensional world, so there are actually not only three, but even more than that forms of accuracy. There is accuracy in any one direction, X, Y, and Z. There is horizontal accuracy, which is a sum of squares of the X and Y accuracy. Vertical accuracy is just going to be your Z accuracy, which also, believe it or not, has two and sometimes more components of vegetated vertical accuracy and then non-vegetated or hardscape vertical accuracy. And then 3D point accuracy, which is combining all three dimensions, X, Y, Z, into a single statistical figure of the accuracy of that point in any direction. And here are some of the numerous formulas that are out there for exactly how to combine those numbers to get to these ones. Now, for the record, I am not expecting anyone to make a practice of using exactly these formulas on a daily basis. This is a little bit complex. It's more about establishing that foundation of being aware that, yeah, accuracy can be in different directions, and it can be very, very different in different directions as well. And many times, that's okay. We do plenty of ALTA surveys where someone's like, hey, your vertical accuracy looks terrible, and they say, I don't care. It can be off by 100 feet. This is only a 2D survey. As long as the horizontal accuracy is good, I'm good. So, all right. But the accuracy totally matters. And then the other thing is accuracy in vegetation. In terms of a real properly analyzed survey, there will be two accuracy numbers, vegetated accuracy and non-vegetated accuracy. Non-vegetated accuracy is typically what people think when they say accuracy because we're talking about hardscape. But especially with the proliferation of LiDAR, LiDAR is becoming so much cheaper for surveyors. With the proliferation of LiDAR, measuring accuracy in a vegetated area is just such a different ballgame. And like I said before, it's not normally distributed or almost never normally distributed. And annoyingly, it can even really change over a site too, depending on different site conditions. Because woods might have different vegetated accuracy depending on the type of tree that's even there and how well the LiDAR can actually penetrate the canopy. Woods will have a different ability to penetrate than low-lying grasses or crops, or maybe certain areas the crops were watered really well and they're so thick that the vegetated accuracy is 5 feet off. Or maybe there are other areas where there was less water on the crops on the same gosh darn site, and it can penetrate perfectly so that the vegetated vertical accuracy in that section is just a few tenths. But this is one of those things where accuracy is not always consistent over a site, and every site is different. Sometimes accuracy varies based on the distribution and quantity of your ground control. If you have all of your ground control points positioned in a specific corner of the site, there's a good chance that the accuracy in that corner is very high quality. But maybe if you took some check shots where you didn't have control, depending on how you did your RTK, what your post-processing workflow looked like, you might have way worse accuracy on a different side of the site. That is totally possible. Same thing with site conditions, whether it's elevation, shadowing, vegetation, and the quality of RTK or PPK at different locations as well. In fact, this is another thing that's becoming more common as drones become more powerful, but are also used over larger and larger sites. People want to take off and they'll fly the drone a mile away from where they took off, and then it'll lose its RTK connection to the base. It'll lose an RTK fix and go into a floating solution. And well, it gets really messy at that point. It might be okay depending on how long it lost link, whether you're using photogrammetry or LiDAR, or it might be far enough away that you have a lot worse data where you lost your RTK link. So that's a little bit about, kind of what accuracy is, but it's also worth talking about the things that accuracy is not, but things that people often have misconceptions of what accuracy is. Accuracy is not equal to GSD, or ground sampling distance. Ground sampling distance is basically the resolution of your aerial map, right? If you fly really close to the ground and you have 1 centimeter per pixel, that does not mean that you have 1 centimeter accuracy. And while they are occasionally related, they are not directly related. You can fly really low, get really, really high resolution, and still have terrible accuracy. It used to be in the earlier days of drone surveying, when very few people had RTK, you were just flying a drone with no RTK capabilities, relying on photogrammetry and ground control points only. There was a good rule of thumb that your accuracy was about 3 times what the ground sampling distance is, the resolution. That was used as a rule of thumb, and so people thought, okay, my accuracy is 3x whatever my GSD was. And that worked pretty well for a while, but that's actually changed a lot now with technology. That number one, if you botch your control and you don't set enough control, accuracy is going to be way worse than 3 times your ground sampling distance. And now, especially with the advent of LiDAR, much more highly calibrated drone-based cameras, and really high precision IMUs and RTK on the drone, you can actually get provable accuracy almost up to the ground sampling distance, right? So if you had a drone that was flying even relatively high at 400 feet and you had a resolution of 7 or 8 hundredths of a foot per pixel, you could actually still get accuracy of 7 or 8 hundredths of a foot. It's pretty impressive now, the way that this technology has gotten. Also, ground sampling distance is not at all, accuracy is not equal to map scale. Again, this is a very generational thing, I want to say, where map scale used to be everything for aerialists, and now for people that myself that work exclusively in digital thing, we don't even have a map printer at our office because we just work with everything on a computer. So the concept of a map scale doesn't even exist until you print it. But map scale, even though that used to be the way that you reported accuracy effectively, is no longer equal to accuracy. Same thing with contour intervals. They used to be equivalent to accuracy. No longer. That's not a good way to talk about it. And in fact, this is specifically mentioned in those ASPRS positional accuracy standards. They do not endorse the use of GSD, map scale, or contour interval to express product accuracy. So the next thing I want to talk about with accuracy is the concept of accuracy classes. I can go over this part pretty quick, because while accuracy classes used to be a bigger deal of class 1 accuracy or class 2 accuracy, they've changed the accuracy classes to effectively be equivalent to what the root mean squared error is that you're seeing. So those RMSE calculations of independent check shots, that's effectively what the accuracy is. And you should set your target accuracy prior to flying a project. I'll talk about that a little bit more in the best practices section of how to set your target accuracy and what kind of target accuracy means. But here's the table of your different accuracy classes, and there are a bunch of other tables of how that applies to older maps and older standards, and what 1 foot contour intervals used to mean and how that relates nowadays to the modern centimeter-based classes. And again, it's centimeter. It's the American society. Why do they use centimeters? Come on, it should be feet. All right. I'd say I'm not going to rant about feet and centimeters anymore, but I probably will. So yeah, just to kind of summarize, what is accuracy? 2 components to accuracy. This is what we're talking about. It's the root mean squared error of independent check shots. That's really the gold standard for how you actually measure accuracy. It's going to be how you certify accuracy. And then now the most up-to-date standards also include the error in your check shots themselves, because it is acknowledging that there is error in the check shots, there's error in the drones. Sometimes one is way bigger than the other. Sometimes one of them is so good that it doesn't matter, right? I mean, if you were doing theoretically a 30,000 foot manned aircraft photogrammetry mission and you had a pixel size of 3 feet, and then you actually surveyed it on the ground with a really long duration OPUS solution, the error that is inherent in the ground system is negligible. It doesn't matter. It's all going to come from the error of the actual system. But that is the most modern standards, is you got to be aware of both of those. Any questions about accuracy or how that impacts in the real world, or any thoughts on measuring it? Anyone else want to give a rant against centimeters too? I'll do it, I swear. All right, so let's get into something. Let's get out of the world of academia a little bit and get now into the world of what actually impacts accuracy. Now, this is still derived. This portion is going to be derived about half from the academic standards that talk about all of the ways that that drone surveys, or any aerial surveys for that matter, can be accurate, more or less accurate. But another half of this comes from the practical side of what are things in the real world that actually lead to better accuracy or worse accuracy or things like that. And there are a ton of things that impact accuracy, but the main categories are, number one, the drone and the sensor. How good of a drone did you buy? How good are the components? How good is the camera, the LiDAR sensor, the IMU, the GPS, etc., etc.? But that is only one component. And in fact, far too many people think that that is the only component to accuracy, that if you spend enough money on the drone, then your survey will be accurate. But that is absolutely not the case, because there are plenty of other things, including mission planning. That's going to be questions like, what's your overlap? What settings are you using on the drone? What flight pattern are you going to take? Where are you going to set your ground control? That sort of stuff. Ground data collection. How good are your targets? What setup did you use to measure your targets? What type of RTK or PPK solution did you use to measure them? Are you using a total solution or a total station? Are your targets set in a way that it's actually visible, or are they set in a bad way that itself introduces error? That can impact accuracy a lot as well. And data processing. Data processing has huge impacts in accuracy. Whether it's photogrammetry, and you need to know if your photogrammetrist actually knows what they're doing and how to actually measure the quality of an aerial triangulation result versus IMU errors that pop up, or camera calibration errors, or being able to spot issues in the skew of the ground control points that you're using, things like that, or all the way to the actual drafting side. This now matters a lot more in LiDAR, where you're doing things like ground classification algorithms. If you do a ground classification algorithm that does a really terrible job of separating grass from dirt, well, you're going to have much worse accuracy than the exact same data set. Same drone, same processing, same point cloud can have two fully different accuracy numbers based on who processed it and how it was processed on LiDAR. As well as the site characteristics totally impact accuracy as well. How big is the site? How far is it from RTK and that sort of thing? How much vegetation is there? What type of vegetation? Is it more rocky? Is it dirty? Is there high reflectivity on the site? Every single one of these things impacts accuracy, and any one of them, if you completely ignore it, can ruin a project. And this, I would say, is actually one of the biggest pitfalls, like I mentioned before, is that people think that, oh, you just need to get one of these things perfectly. No one would ever say it that way to themselves, but we see it in the real world, especially when it comes to the drone hardware, that people want to buy really expensive drone hardware to get the best accuracy. Yes, the more expensive drones typically can get better accuracy. That doesn't mean that they will get better accuracy, and it certainly doesn't mean that they're easier to use. And in fact, that's another big thing. People buy really expensive drones that are capable of good accuracy and then use them improperly. And in fact, everyone here has probably seen that with GPS equipment too, right? You can buy the most expensive GPS equipment on the market, but if you don't use it properly, it's not going to give you the best results possible. So let's talk about drone quality a little bit. If you see these two drones, these are both more common drones these days. Well, if you own one of these, I have some bad news. These are not our favorite drones actually out there. The ones that you see right now, this is going to be the Autel Evo 2 RTK, as well as an older version of the Phantom 4. And I can tell you two separate things about these little ones. These both work for photogrammetry typically. You can get accuracy up to a few tenths and maybe up to a tenth if you're good at everything else. But they definitely run into some issues, whether it's a rolling shutter camera. That means there is some error that, yes, there is software to adjust for rolling shutter issues in photogrammetry, but it's not that great. To the RTK unit on the Autel that doesn't time sync to the image stamps really for interpolating the differences between when the camera was taken and when it actually writes the image, all of that stuff. Or to the Phantom 4, which doesn't have any RTK capabilities at all for the old one, so that means you're relying purely on ground control points. Now, I can't talk that much shade on those. That used to be the only game in town for drone surveying, was you fly something without RTK, you set your control. And honestly, it still works now. But with any modern survey drone, having high quality RTK is pretty great. And so with those, I inevitably get the question of, okay, so what are your favorite aircraft? What are the ones that we actually see the most, that people are most successful with? And again, this is going to be a little bit more field operations biased here than academic, because most successful does not necessarily mean the most accurate, but the most reliably accurate as well. So that's why you won't see some of the highest end ones on here, because they're so expensive and they're actually easy to make mistakes. Believe it or not, our favorite drone right now overall is the Mavic 3 Enterprise RTK. No LiDAR capabilities, it's photogrammetry only, but it's got a 20 megapixel global shutter camera with a very, very competent RTK system, and it's extremely easy to use. So easy to use that I could teach my 5-year-old how to fly the thing. It's really, really simple. And our favorite LiDAR system right now is the very newly released DJI M350 with the L2 LiDAR system. If anyone has heard or seen, the older DJI L1 and said, that LiDAR isn't quite good enough, well, the new one, we've got some, we got our hands on them. They only started shipping this month, actually. So we haven't even published our final accuracy data, but we've collected it, and we are very, very, very impressed by the step up in LiDAR quality between the L1 and the L2. And now it benefits from a lot of the same DJI stuff of just being brain dead simple, easy to use, and reliable. You take it out, and you can be very confident that it's going to collect the right data the first time. But it also still has some challenges because, if nothing else, it's made by DJI, it's made by a Chinese company. A lot of government entities aren't capable of doing that. Our favorite non-DJI drone right now is actually going to be the Wingtra, which I think Cyware even had one of these here at the show. This is one of our favorite non-DJI drones right now. It's more expensive and not quite as good overall as the DJI drones, but it's not DJI. And there are some things that I've been seeing rumors and stuff that they'll be announcing a LiDAR payload later this year, which would be pretty cool. I bet it's going to be pretty darn expensive, but this is a good one, especially if you can't fly a DJI drone or anything like that. All right, moving on to other things that impact accuracy as well. That's the drone, but in addition to the drone, there is obviously the sensor quality as well. Two key things that impact the sensor quality, or two sensors, cameras and LiDAR, that I want to talk about real quick. First of all is the camera itself. Much like when I was saying earlier that ground sampling distance does not equal accuracy, or at least not anymore, a camera cannot be defined, a photogrammetry camera cannot be defined by any one metric. You need to take it as the grand total of all things. You need to think about the shutter that is taken, that is what basically opens in the back of the camera to let the light in. Whether it's an electronic rolling shutter or a global mechanical shutter. Mechanical shutters are going to be better, but more expensive, more rare. What is the resolution? That means how many megapixels is it, right? A 20 megapixel camera is typically good enough. Is a 46 megapixel camera better? Maybe. It kind of depends. In isolation, 40 sounds like a bigger number than 20, so that's probably better, right? Well, yes, but it depends on what lens is mounted on it. What's the overall system accuracy of the question? Things like field of view. In fact, for anyone that has the DJI P1 photogrammetry sensor, that one had, for the first year and a half of that camera's existence, was majorly hamstrung by only having a 35 millimeter camera, which is a quite narrow field of view for a drone mapping camera. Especially because drones are limited to only being able to fly 400 feet above ground. That actually gave it what we almost called a drinking straw effect. It was like surveying by looking through a drinking straw. It saw such a narrow footprint on the ground that even though the camera was of very good quality, the lens was terrible. So if anyone has the DJI P1 though, they finally released a firmware upgrade that'll allow for a 24 millimeter lens support, Upgrade to the 24mm lens, you will be much, much happier. The quality is better. It covers more ground. It's better in nearly every way. I don't like that at all. But lens quality matters as field of view and things like that. Cameras are not defined by a single statistic. It's the overall picture, overall quality of a camera. And ultimately, at the end of the day, it's the accuracy of the survey that matters, right? When you give someone a map and they do all of their check shots and everything checks out within 7/100ths of a foot, no one's going to ask what megapixel camera you used, or maybe they will out of curiosity, but that's not going to impact whether or not the survey is any good if the accuracy is there. That's what you really ought to care about, is the accuracy there? Can you prove it? And can you, once you have the accuracy you need, what's the easiest way to get to the accuracy you need? It's a very similar story with LiDAR, but all of the jargony tech words are going to be totally different. LiDAR is not defined by a single metric, right? Whether it's the IMU and the quality of the IMU and the angular precision there, or the pulse rate. Ooh, this LiDAR has 500,000 pulses per second, and this one's only 250,000 pulses per second. I can tell you 100% from my professional experience, I have never seen a drone survey that failed because the pulse per second rate was not high enough. The point density of LiDAR, of drone-based LiDAR, is so ridiculously high that that has become a meaningless metric. And yet, I see so many companies advertise higher pulse rates. I see so many people buy more expensive drones because it's got 500,000 pulses per second. That's pretty good. That's not what defines a good LiDAR system. Again, it's the accuracy of the final product that you actually care about, which is the totality of all of these things put together. IMU, pulse rate, number of returns, and much, much, much more. Any other questions on hardware before I move away from hardware now? Specific drones or anything that people are curious about? All right, I will keep rolling into the next thing that actually that it really impacts accuracy, which is mission planning. And now we're back into some real world data, which is in our professional experience, about 2/3 of photogrammetry problems are caused by poor mission planning. You didn't fly the right overlap. You didn't fly the right altitude. You flew too close to the ground. You flew way too far away from the ground. You didn't fly over your control points. This is the type of stuff that isn't captured in the academic documentation at all. But this is what really, really makes the biggest difference in terms of successful drone programs and not, is just these basic concepts of mission planning. Things like, okay, what altitude do you want to fly? This is a table that we put together many years ago. It's actually generally targeted towards lower end photogrammetry drones. So that's going to be things like your Phantom 4 RTK or your Mavic 3 Enterprise RTK or other similar 20-ish megapixel drones. This is a table that shows about what accuracy you can expect. And by the way, when I say accuracy, I mean accuracy according to the ASPRS positional accuracy standards of a 1/10 accuracy class. Again, I say 10th, even though they say centimeters, but that's how surveyors talk. You want a 1/10 of a foot of accuracy? Fly at about 150 feet above ground. Or if you're okay with 2/10 of a foot accuracy, which by the way, if all you're doing is 1 foot contours or topo over a 300-acre site or something like that, you'd better be flying at 400 feet. Because if you look at the other impacts of this, things like the number of photos per 100 acres, you can see that the data starts to become very, very, very miserable to deal with. Once you get into the 6,000 photos or even 10,000 photos plus, boy, it gets really tricky dealing with that much data. But knowing your actual mission planning, knowing your accuracy, your target accuracy beforehand is a huge and important thing in terms of getting your site right and getting the accuracy you need the first time and the easiest that you can. Also in mission planning is overlap. And you need to think photogrammetry and LiDAR overlap are very different things. And it's worth noting there are very different requirements for different systems. Traditional photogrammetry, where you are using a lab-calibrated, extremely high-quality camera, you can get away with what a modern photogrammetrist would call extremely low overlap, right? Whether it's 30% overlap from one image to the next, which is something common in very high-quality manned aerial photogrammetry ones. Part of the reason you also have much lower overlap is because the cost of data acquisition, the cost per photo, is often very, very expensive. So you want to do anything you can to cut down the number of photos. Digital photogrammetry, taking another picture is cheap. But also the cameras aren't as well calibrated. So to compensate for that, you take many more photos with much higher overlap. LiDAR is a similar world, actually. With ultra high quality LiDAR systems, you can get away with a very low overlap. With other LiDAR systems, you actually can get the same accuracy as the really expensive ones, but sometimes you do that with just higher overlap. Plus, in our opinion, we like higher overlap for LiDAR because it just gives the sensor more opportunity to penetrate vegetation from different angles. And so you actually do wind up getting a more complete ground surface in vegetated areas when you aren't really stretching the outer limits of what's the minimum overlap you can get away with. As a rule of thumb, we find 75-75 to be a very good Goldilocks zone for digital photogrammetry overlap, 75 front, 75 side. And by the way, you can quibble with me. I like 70-70, I like 70-80, I like 80-70. That's all close enough that there is very little material difference. We find 75-75 to be about the right middle ground. LiDAR, you can get away with less. Yes, question? Correct. So this image would be what 50% overlap looks like, or thereabouts, with the idea that actually it looks like a little bit more than 50. So if you measure, this distance of the left photo and call that 100%, and the place where they overlap, it looks like, yeah, that's maybe about 60% without getting out a ruler or anything like that. So yeah, this would be about 60% front lap. And this is front lap because the aircraft is obviously moving forward in that correction. And then when it comes back in a different flight line, take that same concept, rotate it 90 degrees, and that's going to be your side overlap. So yeah, 75-75 overlap is pretty high. And if you do the math, if every photo overlaps 75 with the next, and then 75 with the side, that means in an ideal, perfectly flat world, any point on the ground can actually be seen from 16 different photos. And that is actually the core of modern digital photogrammetry. You can see it from 16 different photos. You can triangulate it with high accuracy. Not only can you triangulate the image geolocation, but you can actually calculate and correct any sort of image distortion because you have so much information from all of those photos that you don't need to do when you have a lab calibrated camera. Also, before anyone asks, no, it is not worth it to lab calibrate a drone camera. Calibrating the camera itself costs so much more in excess than the entire drone and camera system. And in fact, they're just not even super high quality made. So you put the instant you then throw it into your truck, it hits something and it gets knocked out of calibration. So no, don't calibrate, don't get a lab calibration report on a drone camera, not worth it. Another topic to talk about in mission planning is nadir versus oblique imagery. There are a handful of autopilot softwares that have started to push more oblique imagery. From what I've seen, obliques can offer better identification of vertical features sometimes, like if you're doing the facades of buildings, but it typically comes at the cost of much more processing time and lower resolution. I say lower resolution because the easiest way to think about it, I love this little imagery here, that when you're looking straight down from a vertical side, that's what things look like. But once you start to get more oblique, if you look towards the horizon, the aircraft is going to be at the same altitude, but look how tiny those little boxes are. You actually have a much lower ability to see something, to resolve features. It actually can lower your overall accuracy because you can't see things as well when you're taking oblique angles. Plus, it's not that a nadir image doesn't take things at an angle. It's not like it can't even see under eaves to some extent because the camera is taking an image down like a cone almost. It can already see under things. You have a certain amount of oblique. And as long as you're not doing the drinking straw effect photogrammetry that I was talking about before with the narrow field of view, most drone cameras actually have, let's see, a 24 millimeter camera has an 84-degree field of view, so almost a right angle. You actually are getting very good angular coverage even with straight down nadir imagery. So we typically recommend nadir only imagery. It makes all of the processing and math and analysis much better. I'll put in the caveat, yes, there are going to be some exceptions. And in fact, with this entire presentation, there are going to be rare exceptions to almost everything. I'm hoping to cover, 98% of projects with things like that. So resulting accuracy is rarely improved by adding oblique imagery. It does make things harder to process, and we recommend nadir only. All right, moving forward, mission planning and RTK setup. So this is about the setup of how you actually get your RTK data streamed to a drone. So things like your GNSS base station selection. Are you using a local base station where you set up a site? And this can be either like one that's owned by a drone company, the DJI, they have their own DRTK2 system that works with the Mavic or the Phantom 4 RTK or with the M300 350 series. That actually provides really, really, really high quality, short baseline distance streaming corrections to a drone. It's not going to replace your survey base or rover anytime, but its one job is streaming corrections. It's actually very good at that. Or you could use things like a public base station, or even a network, or NTRIP is the internet protocol for actually streaming a lot of these base station information things. There are a lot of different ways to set up your RTK station. I can tell you what we prefer is have a local base station. I said that before, I'm gonna say it again, have a local base station for drones. Network corrections are really, really good for, like, if you're using, network correction services, real-time networks, anything like that, for ground-based surveying, where you can occupy a point and it sits there for 5 seconds, or maybe more. Or maybe you're taking a 60-second occupation time, or maybe you set it up and it says, oh, error, waiting for fix. Okay, there's the fix. Now I've got my point and you can move on. Drones don't get to do that. Drones are hurtling through the sky at 30 feet per second. If it loses an observation for a single epoch for a single second, it's 30 feet down the line by then. So we have found that even when it has RTK fixed solutions using network corrections, or when post-processing against public base stations, if the baseline distance is more than a couple miles away from the base, we start seeing very, very, very meaningful noise in the meaningful error in the image geolocation solution. So all of that to say, drones are really sensitive to baseline distance, way more so than ground surveying. So if you like your network solution, great. I'm glad you do on the ground. We do not recommend it for drones. Get a local base station for a drone. So yeah, what geolocation setup should you use? And honestly, I have probably been brushing over so far more than I should the concept of drone surveys without RTK. Because there are probably people in this room that are using non-RTK drones, whether it's a original Phantom 4, which was a workhorse drone for a very long time and still produces high quality data. But if you're in the market for any sort of new drone, RTK should be considered a must for any drone for surveying now. It's come so far down in price, so much easier to use. It should be a must, and especially for large projects. Really, if you're doing anything over 20 or 30 acres with a drone, RTK, onboard RTK should be considered an absolute must. Little caveat, I say RTK, PPK is perfectly acceptable. It doesn't have to be real time. Post-processing all of your data can get comparable, if not slightly better accuracies. So forgive me for intermixing those two words for anyone that's particularly nuanced about that. But also it's worth acknowledging there are a near limitless number of permutations of how you can set up your GNSS system. Where the base is, what radio technology you're using. Are you using a first-party base, a third-party base? Is it set up over a known point, or is it set up over an arbitrary point? Will you be getting an Opus solution later, and then will you be adjusting all of your data from the field, and on and on and on and on and on? There are so many different ways to go over it that I can't possibly go through everything. Oh yeah, there you go. That's just what I said there. But the best solution, honestly, depends on your professional expertise. There are some solutions that work on sites that are very well connected and have close base stations. And other times you're going to be absolutely in the boonies and you need a really robust solution. Sometimes you'll be so far out that there might not be a public core station within 80 miles, or at least a public working one, because so darn many of them seem to be offline these days. But yeah, like I said, there's so many different GNS correction systems to use. I'm not going to tell you which one's the best. It needs to apply to each individual project. And like I said, we don't recommend network or permanent base stations only. The baseline distance is just too long for survey quality accuracy on a drone. Actually, I should caveat that too. Survey quality accuracy. Totally depends on what you need. If you're good with half a foot of error, use your network system all day. It's super easy to use and it's robust. If you want to get to that 1/10 of a foot error that I talk about, that's my target for most drone survey projects, don't use network services. Local base station RTK, despite what what a lot of the vendors try and tell you, is just not as good. And then I'll maybe get my commission check when the vendors sell a whole bunch of extra base stations, because that probably gets them even higher commission or something. Yeah, network correction services, good for ground surveying, good for GIS accuracy, not recommended for drones. But what I also get is, all right, we just talked about all of this RTK stuff. Yeah, we got a question? Couple questions?
Yeah, with the base station, you use a VRS solution, also that where it's processed through, have your control line close to the
Yeah. Great question. You can. It is better than just a raw network solution, but still not as good as actually having a physical base station that is on the site. That physical base station that is on the site has the lowest overall baseline distances. Without getting too much into GPS, which I'll admit is not as much my level of specialty, the propagation of tropospheric errors over various miles, while VRS systems can mitigate that very substantially, it's still imperfect, and it comes down to that last thing, like I said, there's zero time-based redundancy on a drone. You can't take the same occupation twice. It is moving and it is gone. If you have anything other than an absolute perfect fix, you are introducing error and there's no way to recover that. You can't take a longer occupation time. It's moving. You can't send the drone back to it because it's flying through the air. It might be off even by whatever. Like you just have to do it. So it works. It's better. It's still not my favorite, certainly. Also, VRS solutions, a lot of them require, high quality internet connections as well. I know there's some with satellites and that sort of thing too, but they can be another finicky point of failure in the field sometimes, especially if you do real remote stuff where you don't have cell service, you can't call someone to help if your things aren't working. It's nice to have a system that's robust enough that it can work fully off the grid and still get good data. I like local base stations for that reason too. So we've been talking about all of this RTK stuff on board, like how do you get all your RTK accuracy? And RTK is really good. Again, RTK, PPK I use mostly interchangeably. So people say, do I need ground control at all? And in fact, a lot of the, again, I apologize for throwing the hardware vendors under the bus too much on this stuff. They'll say, this drone has this great RTK, you don't need ground control whatsoever. That is technically true. Good RTK is technically capable of producing survey-grade accuracy up to 1/10 of a foot without any ground control points whatsoever. But, big old but here, in the real world, in our professional opinion, no control is not good enough and is not a robust solution. Ground control is required for things like properly calibrating the camera, because even if your RTK is absolutely perfect, that tells you where the drone was, and you don't particularly care about where the drone was, you really care about where the ground is. And the vertical error is actually much more sensitive to camera calibration with medium quality cameras than horizontal, but it's really important for calibrating the camera. For localizing your project, maybe you're not over an exact, public datum. Maybe you are localizing it to a known control point. The easy way to do that is shoot your local shots, whether it's a 5,000 arbitrary, or just you set up over a known point and you want your survey to match with all of the other surveys there. Localization makes a big difference for ground control points. And the ability to detect errors. As robust as your procedures might be, all of these procedures are still run by humans. And everyone in this room, I'm sure, has seen a survey where someone set their rod height wrong or insert any number of possible errors. Having ground control points adds a level of professional reliability and redundancy to make sure that if something goes wrong, you can check it. So we think that ground control should be considered a necessity. Now, how many ground control points do you actually need? Our recommendation, and this is for sites that for projects that at least have RTK data, a minimum of 3 per project, as well distributed as possible, and ideally 3 more for any time you move your local GPS base station. These are our recommendations. They are not absolute. And again, it actually starts getting more complicated when I get more into the concept of checkpoints in a little bit. But just having some ground targets is, we think, absolutely professionally required. Having them well distributed helps, but is much less important with the advent of high quality RTK and that sort of thing. This is an example. This is actually the data set that we're going to use for the L2. This was flown with the DJI L2, and it's photogrammetry data, and we actually set a whole bunch of control points here. But this is an example of something that, how good will accuracy be if all you can set are 3 control points? I don't know if you guys can see them that well. 3 little blue dots up in this corner are the only 3 set. Accuracy is actually pretty good as long as your GNSS solution is good. As long as your RTK and PPK is very high quality, you can get away with something like this. But if your RTK fails, then you might be completely toast in these other areas. Good accuracy is still possible, but it's not as robust of a solution. Whereas ideally, I thought I had another slide there with that, but I don't. Ideally, you'd have them much more well distributed, and that gives you not necessarily better accuracy, but more reliability, more operational reliability. As far as how to set targets, the standards of what count as targets really differ among surveyors. We think well-defined points are important. You can take just topo shots, standard just walking, go to natural ground and take a shot and call that a check shot. That works for measuring vertical accuracy. That doesn't work for measuring horizontal accuracy. For horizontal accuracy, it needs to be something that is well-defined. For LiDAR, things like edge of paint stripes are helpful. That shows up in intensity because LiDAR by itself can't actually see color, so you have to rely on something other than color. On the elevation surface, that means that you should set your target flat with the ground, not on a target that is, above or below, right? If you had a table in the middle of a site, don't set your control point on the top of the table. It's much better to set it on the ground, far away from any sort of slopes or ridges or things like that. When setting check shots, you should set them away from your ground control points. If you set a ground control point and then measure 5 check shots that are all right next to it, that's not going to be very robust, and ideally on flat areas of gentle uniform slope. As far as what good and bad targets look like, there are some things that kind of work but aren't ideal, whether it's just like a bucket lid or a flat white piece of paper. It's kind of hard to define the center. Corners are really tricky as well. Chevrons are common. I don't like them because a lot of surveyors treat them differently, whether they're marking the front tip, the inside corner, or the center. I've seen all of those sorts of things. And depending on where you live, there are other targets that I've seen. I'm kidding. If you use those as your GCP targets, wonderful. Please continue. But no, realistically, checkerboard patterns have become far, far, far more common than anything else because they are typically very easy to set. Black and white are still common, which is fine. I will admit, working on the photogrammetry side as a data guy, I don't know why everyone works in black and white anymore. We've had color cameras now for decades, and colors like this are much easier to spot than black and white in an image burn. So I like those. And a last thing, just another comment from the ASPRS positional accuracy standards. In general, ground control accuracies and survey procedures should be established according to project requirements and should be twice, I thought it was quoted on here, but apparently it's not, should be twice the accuracy of the survey that you want at the end. So that means that if you want 1/10 of a foot accuracy, you should target your ground control points to be accurate to 5/100ths of a foot. That is doable with GPS. That is about the upper limit, about as good as most GPS can get, is about 5/100ths of a foot. So generally, if you want 1/10 of a foot, according to the standards, if you want to certify according to the standards, it needs to be twice as good. And then getting on to data processing and how that impacts accuracy. The data processing is both art and science here, right? And this is a quote that I've picked up, that photogrammetry is the art and science of making measurements from photographs. There is no perfect way to process all data because there's so much art to how you massage the various ground control algorithms. When you are drawing points, when you're drawing brake lines, what density of brake lines do you need? If there are tire truck ruts going through the mud, then are you going to draw brake lines on that? Well, if yes, you're going to spend a very long time drawing brake lines on, tire marks. And if no, then sometimes you can have 6 inches of error where the actual terrain follows that. What actually matters, there's really an art to this stuff as well. And the data processing side is a major mix of art and science, right? Whether you're going from the actual photogrammetry and aerial triangulation stuff. This is snippets from a Pix4D quality report. We actually love Pix4D. Pix4D is a completely capable and competent photogrammetry software, as are other softwares out there as well. It's not the only one that works. Plenty of different softwares works. But you have to be able to interpret a lot of this data, whether it is the geolocation variance report so that you actually know when you think you're getting RTK quality, are you actually getting a standard normal distribution of errors in accordance with what you would expect? Is the error of the GPS outside of the range than you would expect, which is an indicator of a likely problem somewhere else. So being able to process the data matters just as much as being able to collect the data. And then on the drafting side, point density, right? Which is better? Having a very accurate point every 50 feet, like you might do with cross sections, where you do cross sections of a road and the cross section, each individual point is accurate to 0.03 of a foot. You shot it with a total station, it's perfect. But you only have one cross section every 50 feet. Or you do a a drone survey there where you have a point every foot along the entire road, but each point might have a 1/10 of a foot accuracy. Maybe it's a 1/10 of a foot accurate. Which one is actually better? Well, some of that comes down to personal preferences and what people are used to. We are actually seeing a shift now. A lot of engineers have been demanding, I want 50-foot cross sections because that's what they're used to demanding. They're just used to it, and so they'll still ask for cross sections, even though generally speaking, having a slightly less accurate point at a higher point density is generally going to be better. Couple caveats there, be aware increasing point density does not make accuracy better necessarily. Just by saying, instead of having a point every foot, maybe we have a point every 6 inches, that doesn't make accuracy any better. And in fact, if you're doing a map of an acre of land and it's completely flat, you probably should only have a couple hundred points to define a flat acre of land, as opposed to 40,000 or 200,000 points, at which point the file size becomes useless. The tin becomes really complicated. You need really expensive computers just to open it. But point density definitely can improve the overall quality. And in fact, here's another slide on accuracy and point density here that really kind of shows this idea that if you have a less dense point on a piece of terrain here, even if these points on this top one are more accurate as individual points, when you actually start measuring the real surface, this kind of red line, against the tin surface, it winds up creating way, way, way bigger errors. So having this higher point density that much more faithfully reflects the surface is generally going to be a better solution there. So being aware of point density selection, either when you're setting up your LiDAR system or when you're actually drafting it and rasterizing and converting all of your data down the line. Another thing that matters, ground classification algorithms. What are you using to actually separate ground from non-ground? This is becoming a way, way, way bigger thing. The more that LiDAR becomes popular, the more that LiDAR data sets are out there. These are so not perfect. There's some amazing AI technologies that are out there, and they're getting better and better every single day. They are still not perfect. Nor can you give the data to a human and expect it to be perfect, because again, it is very much an art. And in fact, there are even just judgment calls that humans make all the time of what even counts as ground versus objects or debris. Is that trash that should be ignored, or is that actually part of the natural ground surface? Same thing with stockpiles, or even, large rocks sticking out of the fact. Using judgment to actually say what is ground, what isn't. An automated algorithm would often take a rock like that and discard it as a non-ground object. Well, if you're actually trying to move something, that's a pretty serious object that you need to move. It's very different than a truck that's parked there. Again, software is getting better and better, but right now, those are just some of the challenges to be aware of, even if technology does eventually help us automate our way out of it. Going forward, the rasterization and vectorization procedures and process, how do you actually go from a point cloud with 1 billion points into then something like this, which is going to be your rasterized surface? Your algorithms really matter. When you actually go from a point cloud and you average it, sometimes you bin your points, you can actually get a final surface that has better accuracy than the individual points of a point cloud by taking the averages. That's back to the magic of statistics, but that really helps. As well as then how and when you mark low confidence areas. There are some quantitative measures to try and define low accuracy areas in LiDAR. I am on the fence about those personally. We'll see how they work in the real world, so can't really swear by them yet. But generally, there's a lot of judgment required when you're looking at data and you are looking at something like this, a profile view of a LiDAR point cloud, and saying, okay, how thin do the points at the bottom have to get before I am confident to say there's nothing there? Or if there's, you know, a 10-foot wide gap in what looks like the natural ground, is that because there's a 10-foot wide object there or a 10-foot wide bush? Or is it actually a slope in the ground that goes up for 10 feet and then down? There's some real judgment for what you would define as a low confidence area based on either elevation, shadowing, things like that. And honestly, it needs to be balanced with a useful map. Making a map is part of that judgment call that's just really, really tricky to do. Going back to then the site characteristics, you know, site characteristics impact accuracy a lot. Clean asphalt. If anyone's done photogrammetry on very clean, very fresh asphalt, it actually does a pretty bad job of it. Photogrammetry needs to pick out little differences and little bits of texture, little plants, oil stains and dirt and debris and paint stripes. But clean asphalt has none of those things, and photogrammetry has a really tough time modeling it, but LiDAR's pretty good at that. Presence of snow and water, different types of vegetation, that's kind of the other insidious thing too, the different types of vegetation. The ASPRS standards have just 2 types of accuracy, vegetated and non-vegetated, but again, this is where a human judgment comes in. It would be very easy to say, okay, on this site, our vegetated accuracy in the wooded areas, I took this screenshot earlier, this is actually the Kalahari Resort right here. This is us, or near us. The accuracy in the wooded areas is really great because the LiDAR penetrated the canopy almost perfectly, we can see the ground. But you know what? We had 3 feet of grass here, and so we know we can see it. It kind of penetrated, it wasn't that great. The point separation between, you know, the 3rd and 4th returns of the LiDAR wasn't very good. So we're going to mark this field as vegetated low confidence, and we're actually going to mark the trees as very high confidence without any sort of area of uncertainty. That's some of your judgment calls that depend on different types of vegetation. But yeah, trees and woods are actually much easier than crops and very dense grass. The site and the sensor characteristics are very much related. Some sensors are good at some sites. Again, photogrammetry, LiDAR being the biggest thing, but also different types of LiDAR sensors. Some LiDAR sensors have extremely high quality single point return accuracy, but not a great ability to penetrate vegetation. Others have multiple returns, but maybe there's a lot more noise, a lot more spread in the overall point cloud. Generally speaking, LiDAR works better in vegetated areas, but for non-vegetated areas or hardscape or dirt, photogrammetry actually remains typically more accurate. Typically, lots of caveats to this, and a lot of people don't believe me when I say it, but I have done enough data to promise you that this is true. In most sites, photogrammetry is more accurate on hardscape than LiDAR. On hardscape. That's a huge caveat itself. Now, are there LiDAR sensors? If you have a $250,000 LiDAR sensor and you say, absolutely not, that thing's precise to 0.04 of a foot because it's got this, you know, XYZ insane IMU on it, you are probably correct. A $250,000 LiDAR sensor will be able to outperform a $5,000 photogrammetry drone. But in most cases, drone-based photogrammetry actually remains both more accurate and way more affordable on hardscape. So don't think that LiDAR is going to solve every single problem. Maybe eventually it will, but it's not quite there yet. Photogrammetry is still the best way to do a drone survey. And then project size too. The larger the project, the harder it is to map it accurately, as well as major elevation changes can make a difference too. This is a site we had to do some photogrammetry on that was brutal on like the edges of the Grand Canyon with almost 1,400 feet of elevation change, which is the type of thing that just materially impacts accuracy. Depending on where and how you fly, our accuracy was absolutely great at the top of the canyon rim, and then atrocious towards the valley when it was getting so much further away from the drone, and there were a lot more shadows and harder angles. But I mean, to answer it, what impacts accuracy? It's almost everything. Like, you could have, while the drone is flying, a particularly fat, juicy bug hits one of the propellers, gets bug guts stuck on the propellers, introduces an unknown vibration that confuses the IMU and causes bad accuracy, right? Like, that is totally possible. Am I going to stand up here and say, well, because of that, you should never fly a job site where there might be bugs? Like, that'd be insane. No, almost anything can impact accuracy. And honestly, there are lots of things that could impact accuracy that I can't think of and the most brilliant scientists haven't thought of. It's impossible to think of everything, which is why measuring accuracy actually matters and is very important. So let's get into actually measuring accuracy now. How do we take all of this that we just learned about how to get accurate surveys? Now we've done our survey, how do we actually measure it? And we're going to jump back from the more real-world side of things into a little bit more of the academic side again here. So again, accuracy, as we've talked about, is the RMSE of independent checkpoints. That's at least the first and typically largest component of measuring accuracy. Like I said, calculating it is intimidating when you look at the formula, but there are spreadsheets that can do it very easily, or softwares that can do it too. This is one from Pix4D, where at the bottom it actually has the root mean squared error of the GCPs and checkpoints. Little caveat thing here, just one little red flag to look at. Pix4D reports the RMSE of ground control points often. That is a valid metric to look at because if there is error there, it is very indicative of error somewhere else in the project. But the error on the ground control points is very different from the error on the check shots. In fact, you will often see a Pix4D quality report that says the RMS error on the ground control points is a few thousandths of a feet. And I promise you, your survey is not a few thousandths of a foot accurate. In order to do that, you need independent checkpoints. So the difference between ground control points and checkpoints is not that they are actually set different on the ground necessarily. Ground control points are marked targets that are used in the creation of a map, and check shots are marked targets that are not used in the creation of a map. That's really the whole difference between ground control and check shots. So to jump back into the practical side, when you're in the field, if you just set a handful of targets, you don't even have to decide then what is a ground control point and what is a check shot. That is up to the data processor to decide. And in fact, here's another one of those tricky things that the academics don't really like. If you run some analysis and say, ooh, there's some error in this, I wish I had more control, you take some of things that maybe were check shots and flip them over to ground control points and start using them to control your project, to calibrate your camera. That can actually help improve the accuracy of your project. Now, you can't then use that checkpoint to measure or certify your accuracy if you're going to the absolute top tier accuracy certification, which again is a very high bar. But ground control points and check shots in the field, you're just shooting a marked point. And you can figure it out later whether or not you're going to use it as a GCP or a check shot. Any questions on ground control or check shots or that sort of things before I keep moving? Cool. Real quick thing for measuring and marking LiDAR control points. LiDAR does not have colorization by default. Any LiDAR that has a colorized point cloud typically gets the color applied to it from a image sensor that was flown with it. That's how things like the DJI sensors work, or the Rock Robotic ones, or that sort of thing as well. The colorization that is applied to a point cloud typically introduces additional horizontal error into it. So a lot of times you see LiDAR point clouds have pretty high horizontal error. LiDAR can be very accurate vertical, but has a lot of horizontal errors, particularly in 2D features, which is another reason why photogrammetry is better than LiDAR on a lot of hardscape features. It can see 2D much more accurately. I always love putting this one up because I actually took the time to make sure that this picture of all black points is exactly the same place as this target, even though it completely doesn't matter at all. But yeah, the colorized point cloud, that's a photogrammetry derived point cloud on the left and a LiDAR one on the right. Some people recommend 3D targets where you actually have either pyramid shapes, or sometimes there are these things that you set on top of a tripod that have like a little star shape, and their LiDAR sensor can pick it up and use it as control. Those absolutely work from a technical standpoint, but are so expensive and cumbersome in the field that we find them to be generally impractical. So we don't really recommend them. Using things like intensity data can actually really help for 2D control, as well as using the colorization of point clouds there too. Oh, here's the slide that I thought was earlier. GCPs and check shots, according to the standards, should be twice the target accuracy of the final product. So if you want to have a map with an accuracy of 1/10 of a foot, your ground survey should have a target accuracy of 5/100 of a foot. So how accurate is your ground data? I just picked a Trimble R10 because I've seen plenty of those around there. And there you go. A Trimble R10 has a precision, and I actually love this, they are very good at this, that they talk about the precision of this system, not accuracy, which is correct, of 15 millimeters vertical, which is 5/100 of a foot, or very, very close to it. And that means that if you're just shooting with the Trimble R10, you are perfectly set up to get 1/10 of a foot accuracy according to spec. As well as, you know, a lot of people then overstate different things. This is your chart from your taking your Opus solutions if you are doing post-processing based on your occupation times and what kind of error you're seeing depending on the time. So if you're actually looking here to get to that 1.5 centimeter mark, which is 1.5 centimeters is going to be about that 5/100 or so, you actually need a session duration of a little bit more, between 3 and 4 hours, if you really want to get an Opus solution that is that accurate. A lot of people think, and again, we're talking statistical accuracy here, the average mean accuracy of an Opus solution is going to be better than this, but it's a statistical thing. You don't know how much worse it is. So that's, people often overstate these accuracies. Talking a little bit more about vegetated versus non-vegetated vertical accuracy oversight. Non-vegetated vertical accuracy, when you're measuring that, is you set a whole bunch of check shots where there is no vegetation. And vegetated vertical accuracy is where you set check shots in vegetation. To perfectly match the highest quality standards, you need to set check shots in both vegetated areas and non-vegetated areas. But the thing that really makes it nasty is just there are so many different types of vegetation on a single site. So here's some photos of another of the site that we're going to do, or that we have flown with the